Now that we've seen examples about how to solve sine alpha equals a number, let's see how this comes up when we go to solve for triangles. So let's say we have a is 7, b is 5, and beta is 25, and we want to find all the triangles that satisfy this condition. So I'm going to start by writing the law of sines and seeing if I can use it. So sine alpha over a is sine beta over b is sine gamma over c. And what do I know? Well, I know a, and I know b, and I know beta. So in this first law of sines, there's only one unknown, and I'm going to try to solve for it. And so sine of alpha, if I multiply both sides by a, I get that this is sine beta over b times a. So this is sine 25 degrees over b, which is 5, times a, which is 7. And so sine of alpha has to be equal to 0.59, and I'm going to round here, 0.592, really it's 0.59166, etc., etc. And although I'm writing this down and I'm rounding it, really in my calculator I'm storing this answer, 0.5916655, so I don't get as much round off error as if I were to approximate this by rounding here. But in any case, I need to find the solutions to this equation, sine alpha equals 0.592, with alpha being between 0 and 180 degrees. One small technical point here is I've put less than or equal to here, where really it should be less than, because you can't have a triangle with an angle of 180 degrees. So now at this point, I'm going to use my skill of solving sine alpha equals a number. I'll use the inverse trigonometric function to get my first, and in my calculator I'm typing alpha 1, well, not typing alpha 1, but I'm typing sine inverse, really I'm putting sine inverse of answer instead of sine inverse of 0.592, and that's giving me a result of 36.275. And I'm going to give myself some room on the right hand side here. I'm going to copy this and move this because we have a second solution, alpha 2, which is 180 degrees minus alpha 1. And so this is going to be 143.725. And both of these are in degrees. Make sure when you're doing this, if your problem is in degrees, which most of the law of sines problems are, that your calculator is also in degrees. And at this point, I think it's important to go ahead and pause and briefly discuss what it means that we got two solutions here. And what it means is that we have a possibility of having two triangles with these conditions that a is 7, b is 5, and beta is 25 degrees. For those two triangles, a, b, and beta will be the same for both of those triangles, so let's go ahead and draw them. And this drawing won't be to scale, that is, it won't reflect which angles are obtuse or acute. I'm going to draw them the same. I just want you to have a visual that indeed, if this is a, this would be the first alpha that I saw for, and then this a would be the same in your second triangle, and this alpha would be alpha 2. Also, the things that are going to be the same for both triangle are b and beta. There's not going to be a beta 1 or beta 2, but there could be a gamma 2 and a gamma 1. So when we write that alpha 1 is 36.275 degrees, we're saying, hey, this is alpha for my first triangle, and when I write alpha 2 is 143.725 degrees, I'm saying, hey, this second alpha is the alpha for my second triangle. Okay, so now we have alpha 1 and alpha 2. We have our two solutions here. And we can continue. We can find our last angle, which for our first triangle, I'll label gamma 1, and for our second triangle, I'll label gamma 2. So gamma 1, that's going to be 180 degrees minus beta minus alpha 1. In my gamma 2, that's going to be 180 degrees minus beta minus alpha 2. When I do this calculation for gamma 1, I get 118.725 degrees. And for my gamma 2, I get 11.275 degrees. Now, an important concept here for the future, when you write down your two solutions, using the skill that we just developed, solving sine of something equals a number, you're almost always going to get two solutions, 1, 2. Of course, there's the chance that you're trying to solve sine of an angle equals a number that's bigger than 1, something like 1.5, in which you would get no solutions. And then there is a small chance that you get sine of alpha equals 1.0 on the right-hand side, which will actually only give you one solution of 90 degrees. But the majority of the time, you're going to get two solutions, alpha 1 and alpha 2. However, there will be a large percentage of the time when you go to compute gamma 1 and gamma 2, and what will happen is gamma 2 will end up being negative. In this case, it's not. We have a positive angle. When you do get a negative, however, that indicates to you that there is no second triangle. So if you're working a problem, you do some calculations, you get your two angles, and then one of them is negative, then you just erase that triangle. So if this had been negative 11.275, I would stop doing any calculation with my second triangle and make the conclusion that there's only one triangle. We'll do an example like that, but in this case here, what we have right now is we have two triangles and we have figured out almost everything. We figured out what the gamma is for both triangles. We figured out what the alpha is for both triangles. So all of this information that I've written on both my triangles, triangle 1 and triangle 2, has been solved for. The only thing left to solve for is C1 and C2, and we can do that using the law of sines. Going back to our law of sines, we'll see that what we have so far for both of our triangles is that we have alpha, beta, A, B, and gamma. And so we can solve for C, and let's see what information is given, B and beta. So I'm going to use this quantity is equal to this quantity because B and beta is something that's given, whereas alpha is something I figured out. I did indeed figure out alpha, but it has some rounding, so I want to make as little round off error as possible. Again, that's not a huge deal. You could use the other equation if you want. You could use sine alpha over A equals sine gamma over C. But I'm going to use that sine beta over B is equal to sine gamma 1 over C1. Now, if you do use sine alpha over A, remember that you need to use the alpha for your particular triangle. So this needs to be sine alpha 1 over A, and you don't need to put A1 here because A is the same for both triangles. Although you certainly could put A1, just know that A1 is going to be the same as A2. Reiterating why is because A is given to be 7 for both triangles. It has to be 7. Same for B and beta. You could write beta 1 and B1 here, but beta 1, it has to be the same as beta 2. However, C1 is going to be different because that's not given information. That's information that we're figuring out. So we have that sine of, and I'll probably need some more room. And I think I'll go ahead and solve for C1. So multiply both sides by C1 and then move this quantity here to the other side. We get C1 is B sine gamma 1 over B. That's not quite correct. Should be over sine beta. And so C1 is equal to 5 times sine of gamma 1. Gamma 1 was 118.725 divided by sine of beta, and beta was 25 degrees. C2, I'm not going to write the sine equation because it's the exact same except these are replaced with 2's here. C2 is b sine gamma 2 all divided by sine beta. And so that's going to mean that C2 is 5 times sine of gamma 2. Gamma 2 was 11.275. All divided by sine 25 degrees. And so my C1, the C for my first triangle, is 10.375. And my C2 ends up being 2.313.